So we're in this chapter. This is our second lecture on combustion and reacting mixtures. We've reviewed a lot of topics from chemistry, the background. One thing we haven't gotten to is air-to-fuel ratio, so let's talk about that. You can either do it on a mass basis or a molar basis, and then we'll continue adding topics. So the air-to-fuel ratio, if you have A to F or if you have A to F bar, which one do you suspect is on a molar basis? The bar. Yeah, this is a molar. And this would be on a mass basis. So it's defined as the mass of air divided by the mass of the fuel. So how many kilograms of air or pounds of air do I need for every pound of fuel that's going into some engine where there's some combustion occurring? Well, how would I calculate the mass of air? Well, if I knew the number of moles of air, I would multiply by the molar mass of the air, and wouldn't that give me the mass of the air? And the mass of the fuel, if I said, well, the number of moles of the fuel times the molar mass of the fuel. Well, we wrote our equation such that the number of moles, everything's done on a 1 kilomole basis of the fuel. So often in this calculation of the air-to-fuel ratio, that is equal to 1, the number of moles of the fuel. So all you have to do is say, well, how many moles of air? What's the molar mass of air? Something like 28.97. Then what's the molar mass of the fuel? You just look that up. Roughly, you can approximate it for each carbon. Basically, it's a 12 kilograms per kilomole. And for each hydrogen, it's a 1 kilogram per kilomole. So you can estimate the molar mass pretty well, but you can look it up to get 3, 4, 5 significant digits on that molar mass of the fuel. If it's on a molar basis, then it would be simply the number of moles of air per number of moles of fuel. Make sense? That's pretty easy to do. Let's continue on. Sometimes they'll say, do a dry product analysis. Well, when you see the word product, what does that mean? That's after combustion. It's what's not the reactants, it's what's coming out in the exhaust. It's the products. And what about dry? What does that mean? Well, we know that the hydrogen went to make water. And usually that goes out in the gas or vapor state. A lot of times the book will use this G, the meaning, oh, it's going out in the gaseous state. But if you have a lot of water going out in the exhaust products, it can easily condense. And so a lot of laboratories that want to analyze the products of the exhaust products, the products of combustion, what they'll do is they'll first dry out the gas. They'll get rid of all the water vapor. They'll cool it to condense it, and they'll put it through a desiccant, and then they'll get rid of the water vapor. And so you'll see that this, a lot of times they'll describe the dry product analysis. And so it's basically just the molar analysis, give me the mole fractions of all the components that are in the products, except you've taken and dropped out that water vapor, and you can just think of removing it by the combination of some condensation, getting it cold, as well as some flowing over a desiccant that absorbs it. All right, so that's a dry product analysis. Ready to solve a problem? So until we apply it, it's all just abstract. Let's apply it. An engine burns octane. Octane is C8H18 completely. So it burns it completely with 150% theoretical air. For part A, determine the balanced reaction equation. C8H18. We leave nothing in front of it, which means there's a 1. Stoichiometric coefficient of 1 in front of the fuel. We're going to pick up oxygen with the right proportion of nitrogen from air, our standard air. I leave a little space right there so that I can fill in the coefficient. Then I come over here and I say, well, I'm going to have carbon dioxide. I'm going to have water vapor. I'm initially going to have no unused oxygen, but I'm going to have the nitrogen that goes through the system. I then say I can get the stoichiometric coefficient in front of the CO2 by balancing the carbons. So if I balance the carbon, what is the coefficient goes in front of the CO2? 8. I can get the coefficient that goes in front of the water by balancing what? Hydrogen. I look at that very carefully. 9. 9 is the right number. All right, go slow right here. I have to balance the oxygen. It's kind of a backward balance, but that will give me the coefficient in front of the air. Okay, so I go slow. I say, how many oxygens, not O2s, but O's, do I get from CO2? 8 CO2s? 16. Then I add to it how many I get? Oxygens? 9. And I get 25. Did I do the math correctly? So I come over here. Sometimes I'll write it as 12.5. Or I'll put it as 25 over 2. I like to put it as 25 over 2 because it forces me to remember the 2 that exists right there. Right? That's really what I'm saying to myself, to help myself remember it's 25 over 2. I need 25 of them, and they're coming from the O2s. Okay. That will then have 0 here, and we'll have 3.76 times 25 divided by 2 oxygens. Is that 100% balanced theoretical error? I have not considered 150% theoretical error. I first get 100% theoretical error. Is it stoichiometric error? That's another way of saying it. They say, oh, it's stoichiometric error. Is it? The perfect amount of error. Because I'm going to modify it, but if I have an error at this point, I'm not going to, somehow heal itself. It's going to just perpetuate an error. So if I want to have more, then guess what goes right here? 1.5. Doesn't that give me 150% theoretical? All right, now, did I change the amount of carbon in the reactants? So do I change the number in front of the CO2 to rebalance? Nope. No. Did I change the number of hydrogen in the reactants? No. Do I change the 9 in front of the H2O? No. So the carbon and the hydrogen are balanced. It's just that I need to rebalance the oxygen because I didn't use up all the oxygen. So what do I pick up for a coefficient in front of that oxygen? So we'll do the 25 divided by 2, and we'll put a 0.5 right there. Right? It's like I bust this into the sum of 1 plus 0.5, and I used up the 100% perfectly, left over the 50%. All right. Do you agree with this or not? Yes or no? Good. How do I modify the nitrogen? 1.5. We're done. So this is the answer for the first part, part A. Let me get rid of some junk here. What's part B say? Give me the dry molar analysis. What are they asking for part B? What are they asking for?
Molar analysis without the water.
Molar analysis without the water. We've done a molar analysis before. They're asking, what is the mole fraction, not of vapor, of the CO2, and the mole fraction, not of the water. Man, I keep messing up. The mole fraction of the oxygen and the mole fraction of the nitrogen. And if I sum those 3 mole fractions, it'll be 100% because I'm looking on a dry basis. I drop out the water. I get rid of the water, and then I do the molar analysis. Okay, how do I calculate the mole fraction of the oxygen in the products? Or let's do carbon dioxide first, CO2. How do I calculate that?
CO2 divided by moles of mixture.
Exactly, that's it. It's the moles of CO2. So we'll have 8 moles or kilomoles of CO2, and then we'll have the 8. Now, sometimes it's better to go ahead and crunch a number. So if we crunch a number, we find that this is 6.25 kilomoles of oxygen, 6.25. And this is all 70.5 moles of nitrogen, 70.5. So you get that it's 8 divided by the sum, which is 84.75, or the mole fraction, I'm going to write the answer up here, is of CO2 is 9.44%. Around 10% is carbon dioxide. Does that look reasonable? All right, well then what's the oxygen? Well, the mole fraction of the oxygen in the dry products would be 6.25 divided by the sum, 84.75. And that comes right in for the oxygen at around 7.38%. And then the mole fraction of the nitrogen would be the 70.5 divided by 84.75. And it comes right in at 83.19%. How would I check them? I would add all those 3 up and see if they give me 100%. They should be close. Does that look good? How about the next part C? Give me the air-to-fuel ratio. Air-to-fuel ratio. Does it say the molar air-to-fuel ratio or just the air-to-fuel ratio? Just air-to-fuel. Is that on a mass basis or on a molar basis? It's a mass basis. It's on a mass basis. So to calculate the air-to-fuel ratio on a mass basis, the mass of air divided by the mass of fuel. So we just worked that out. So I need the number of moles of air times the molar mass of air divided by the number of moles of fuel times the molar mass of fuel. And you'll always do everything with 1 on the stoichiometric coefficient in front of the balanced reaction equation for the fuel. And you have to look up the molar mass of the octane. The molar mass of the octane is 114.22 kilograms per kilomole. Okay. The molar mass of the air is 28.97 kilograms per kilomole. The hard part, the error-prone part, where a lot of students will make an error, is saying for each kilomole of fuel, how many kilomoles of air do I need for that reaction? I'm going to pause. I'm going to walk around the room. I'm taking you right up to the cliff. All right? Right here, you got to get this right. Calculate it and show me the answer. Well, all right. Who multiplied 1.5 times 12.5? What number do you get? 18.75 times what? So basically, I need to bring in 18.75 kilomoles of O2. How many kilomoles of N2 do I also bring with it to get in the 18.75? The 18.75 times 3.76. So really what I'm doing is I'm bringing in 18.75 times 4.76 kilomoles of air. And most people will leave out. Is that what you left out? Yeah. You left out the 4.76. Right? Well, you can do it another way too. You could say, forget using this as the molar mass of dry air based on 21% oxygen, 79% nitrogen. You can do it, probably a few people tried it this way. They say, well, what's the molar mass of oxygen? What's the molar mass of nitrogen? Okay, then I'll find out how many moles of oxygen I had to bring in to combust 1 mole of fuel with the molar mass of the fuel. And then how many moles of nitrogen do I have to come? You'll get the same exact answer. All right? So let's finish this one out this way. And so how many moles of oxygen do I? Well, it's 18.75, isn't it? And then how much the molar mass of oxygen? That one you got to look up. It's 16 and 16, around 32. 32. And then how many moles of nitrogen? 3.76 times the 18.75. Molar mass of nitrogen, 1414, around 28. And then we'll divide by the 1 times 114. It seems ridiculous. I should put more digits on this 32 and then more digits on the 28. But if you run that number, what do you pick up? To 3 significant digits, what do you pick up? 22.6. Right? Now maybe that makes more sense to say, look it, I have, I didn't do the numbers here. Let me just write it in equation format for dry air. 1.5 times 25 divided by 2 times 4.76. I can't hardly squeeze it all in, sorry. But that number right there will give you 22.6. All right. How many people are engine buffs? There's a few engine buffs, right? Anybody heard when you're tuning an engine, the air-to-fuel ratio? What is it for standard gasoline?
14.7.
That's right. Now let's do this. This is our standard octane, right? So just get rid of the 1.5. Take the 22.6 and back out the 1.5. What do you get? It's 15. 15. It's around 15. But what exactly is it? 15.06 or 15.1. And that's with ISO, that's with 100 octane gasoline. That's with your pure, and now most of us don't have 100 octane gasoline. We have something less, so it's not pure octane in our gasoline, and so it's more like 14.7 for the blend. How many people? You remembered 14.7? You remembered 14.7? You remembered 14.7? Who else? Anybody else? But this is a common number, that you may see when you have engines and you're tuning them. So anyway, but here we're running with excess air, aren't we? So that air-to-fuel ratio on a mass basis is 22.6 for this problem. Okay, that took me a little more time than I anticipated. Ready for part D? Calculate the mole fraction of water in the products. It's not the dry air products or dry products. It's the total products. What is the mole fraction of water vapor in the products? Can you calculate it, or you want me to just calculate it and you watch? You go for it, Professor. It's like, all right, let me do that. So what I would do is I'd say the mole fraction of vapor in the products. Well, I have 9 in my standard reaction equation, 9 kilomoles of water vapor. And then I have 9 plus, and I already added these numbers up, so might as well reuse them, 84.75. True? And that gives me certain a mole fraction of water vapor in the products, which comes in to be 9.6%. 10% by, the mole fraction is 10% water vapor. Is that a lot of water vapor? Yep, sure is. Let's move on. What is the amount of water produced? I just did that, didn't I? No, I want it in kilomoles of water vapor produced per kilomole of fuel used. How would you calculate that? Well, you would just say how many moles of vapor per mole of fuel. That's what they're asking us to calculate, isn't it? For part D. It's how many kilomoles of water are produced per kilomole of fuel. So what does that answer equal to? 9. Sometimes the questions, you just have to know what they're asking and make the observation. Like 2 people are in the room. How many people are in the room? 2? Yeah, you're right. Okay, let's move on. All right, now the next question, though, is what is the amount of CO2 produced, but not in kilomoles. It's how much CO2 produced in kilograms per kilogram of fuel. What are they asking me to calculate there? I'm going to just tuck it up here because I don't want to scroll around. Isn't it the mass of CO2 divided by the mass of fuel in our standard combustion equation? Wouldn't that be our number of moles of fuel times the molar mass of the fuel? And then we have the number of moles of CO2 times the molar mass of the CO2. Now we go to our standard reaction equation. For 1 kilomole of fuel, that fuel has a molar mass of, I forgot it already, 114.22. How many moles of CO2? 8. And then I have to look up or remember the molar mass of CO2, 44.01. And so the mass of CO2 produced per mass of fuel is equal to 3.08. What? You mean I take 1 kilogram of fuel, I combust it, and basically going out the tailpipe is 3 kilograms of CO2? Hold it, it's like grown in mass. This is a great CO2 belching machine. That's what we're doing. When you combust the hydrocarbon, you're throwing out. Because CO2 is mostly the oxygen. It's heavy. It's the CO2. Carbon is 12, but each of the oxygen is 16. So that's why it's so big. That's why that number is 3.08. Okay. Last one, what's the dew point temperature? You have to work on this one a little bit. Think about, I take that product out and I cool it until it hits a particular temperature, and that's going to start condensing the water vapor. That's called the dew point temperature. What is the dew point temperature of the products? Pardon? Should I give you a few minutes? Or is it too close to Friday? Are you burned out? Professor, we asked you to do the talking, we'll do the listening. We'll do a really good job of listening if you do a really good job of talking, so try it. All right? Is that what you want? All right, that's what you want. Well, what I have to do is I have to remember that the saturation pressure of water vapor at that particular dew point temperature is equal to the actual partial pressure of the water vapor in the mixture. Hey, I know how to calculate the actual partial pressure of the water vapor in the mixture. Isn't it the mole fraction of vapor in the mixture times the total atmospheric pressure? I'm assuming it comes out of the tailpipe at atmospheric pressure. All right? So we just calculated the mole fraction that vapor is in the mixture. That mole fraction of water vapor was about 9%, right? 0.0944. We multiply by 101.3 kilopascal, and we find that the partial pressure is 9.73 kilopascal. Now it's just tell me the saturation or the temperature at which you get the saturation pressure of water to equal 9.73. That's the dew point temperature. So you go to the table A2 and you find temperature as a column, Psat as a column. Let's get it in the kilopascal even though it's in bar. And we find that it's between 9.593 kilopascal at 45 degrees C. I already put the degrees C up there. And 12.35 kilopascal at 50 degrees C. So we say, hey, 9.73 is in between. You are all experts at interpolation by now. linear interpolation. And so you find the dew point temperature to be 45.2 degrees C, and that's the dew point. True? They say it's going to get cold tonight, tomorrow morning. How many people are going to enjoy that? They're going to go outside and they'll go blow their breath like they're smoking. Remember that when you were in what is it, first grade, second grade? Hey, look at me, I'm smoking. Right? Well, that's what's going to happen here when we really have cold days. All right. The air temperature is so cold. All right. I don't think we have time for this problem. But we do have time for this problem. A lot of times they'll just have a general hydrocarbon combustion reaction equation. They'll say the general fuel is a C with the coefficient A, letter A, meaning A could be 2, 3, 4, whatever. And H, well, with the subscript B. B could be whatever, 4, 8, 10, I don't know. It's general. So if you had this general fuel, this general hydrocarbon fuel, give me the general balanced reaction equation. Which of these would you first be able to determine? This one, this one, this one, or this one? Do the carbon first. All right. So now we're going to do the carbon first. What's that coefficient in front of the CO2? You're good. It's a A. Which one do you think you want to do next? The C? Hydrogen? Do the hydrogen? All right, so what's the coefficient in front of the hydrogen? B or B over 2? B over 2? B over 2. Now which one do you want to do next? The one in front of the air or the one in front of the nitrogen? Let's do the oxygen balance to determine the coefficient in front of the air. What is this one? I pause, I walk around. That's the hardest one. It'll give me more time to think while you struggle. Give me that general equation. Oh, somebody already got it. Shh. Hey, why did you do that so fast? How did you do it so fast? That's pretty good. Most mere mortals take more time to do that.
Simplify.
All right, so it is algebra. That's all it is, but you have to be careful in it. And you pick up A plus B over 4. And for those who have really struggled with this one's the easy one. Let's rebalance the nitrogen. What's the coefficient for the nitrogen with the 3.76, just like that? A plus B over 4. All right, so that's the general combustion reaction equation. Sometimes in this chapter you'll see these A's and B's float around with this general reaction. Now, we've got just enough time to introduce how would we do the first law of thermodynamics for a reacting system. How would we analyze some hydrocarbon fuel coming in with some air, combusting, coming out with some carbon dioxide, some water vapor, a lot of nitrogen, and maybe some other stuff. But everything over here is a R, and everything over here is a P. What's the R and the P stand for? Reactants, products. And so inside the box you have combustion occurring. So could you write down a general statement for the conservation of energy for a reacting or a combustion system? How would you do it? This is one of those things where I really encourage you to walk away from, because it's like, I have confidence, I can do that. You go back to chapter 1 of the textbook and you say, what's the first step? Identify the system. Do I sound like Professor Creamy? Identify the system clearly. How do we identify the system clearly? What do we use in our schematic? You got it. A dashed line that encloses the system. Now, that's the focus of the study. Some things can come into the system and go out of the system. In general, if we're doing an energy balance, sometimes this comes into the system. What is that? Energy transfer by heat transfer. Sometimes you get this going out of the system. Energy transfer by work out of the control volume. And then you have energy transfer with mass flow. The reactants come in. What do they carry with it? It's going to be internal plus flow energy equals enthalpy. So we have the internal plus the flow work gives us the H, plus if you don't neglect the speed of the flow or the elevation of the flow, you could get the kinetic and the potential energy. But often they're neglected. And for the products, we would have the same thing. Enthalpy, kinetic energy, potential energy. True? With that hint, write down the first law of thermodynamics for this system. Or should I just finish it out? The time rate of change of the energy in the control volume. Most of the time it's steady state. That term is zero. But in the general grand scheme of things, if it was accumulating energy in the control volume, that'd be a positive quantity, wouldn't it? But most of the time we analyze steady state behavior. It's the rate at which it's flowing in with the heat, plus it's flowing in with the reactants. They're carrying with each reactant the enthalpy, the kinetic energy, the potential energy. Maybe we think in with the reactants. We'll do I for flow in, and we'll do a sum over all of the R's. Oh, this notation get very confusing. The subscript I for the in, with the sum over all the R's, all the reactants. Then we have minus W dot CV. That's a flow out, isn't it? We also have a minus. We can do the same thing. We're going to sum over all the P's, over all the products. The mass flow rate that exits with the enthalpy and the kinetic energy and the potential energy of everything that's exiting. Now we can start striking terms and saying, why is this equal to zero for a lot of problems? Steady state. All right. Why do we often just forget these terms? We neglect changes in kinetic and potential energy. It's very common to do that. Okay. If you do that, then we get this equation. 0 is equal to Q dot minus W dot C. Now, you say mass flow rate's true, and we've used a lot of mass flow rates up to this point. But then somebody says, I just wrote that balanced reaction equation, but it wasn't in terms of the mass. The stoichiometric coefficients were in terms of the moles. So can we write this not on a mass basis, but on a molar flow rate basis? Would we put N dot in? What's the difference between M dot and N dot? Mass flow rate, molar flow rate. What would be the SI units on the N dot? Kilomoles per second of that species. And then how do I adjust for the enthalpy? You're so good. H bar, right? And we want to sum over all the R's, reactants, and we want to sum over all the products of the same thing. The molar flow rates exiting times the enthalpy exiting on a molar basis. Does that equation look good? Sometimes I'll write an equation and I'll have an error.
Wouldn't the molar flow rates be equivalent?
Well, we go back to our balanced equation. We say, oh, we got 8 kilomoles of oxygen or carbon dioxide going out. We have this many kilomoles of this much going out, right? So do this, take that equation and multiply by, or divide the whole equation by the molar flow rate of the fuel. Think about this. We've done this before. We have 1 kilogram of this working fluid going through the turbine or something like that, or through the heat exchanger, something like that. Here, let's pin it all back to the fuel. Kind of everything goes back to the 1 kilomole per second of the fuel flowing through this reactor. And then we'll have per kilomole of the fuel. And then we'll have per kilomole of the fuel flow rate like that. See? Now, this is where the book, I wish they would have done something a little different. But they rewrite this equation, and they leave 0 is equal to Q dot divided by N dot F. That's fine. They leave W dot CV divided by N dot F. That's fine. And then they do the sum over the products N H bar I. Then they do minus the sum over the reactants N E H bar E. What is that NI? What is this?
Oh, that's the number of reactants. It's like mole fraction for different species.
Well, it's defined as this, isn't it? So it's the molar flow rate in of that individual reactant per kilomole of the fuel coming in, right? So what is that N in terms of something we've been reviewed from chemistry last time? I want the name of it. I don't want to give you the name of it. I want you to tell me the name of that. It's so simple. Oh, I just messed up. See, it didn't take me long. I knew I'd make a mistake. So it's an R for the reactants, thank you very much, and P for the products. And so the reactants are coming in. Yeah, I have that straight. And the products are exiting with the E's. Okay, I've got that there. Thank you very much for that correction. But let me ask you this question before you. I'm looking for the name of N. It has a name that we've been introduced to. But how about this? What are the SI units on that? Dimensionless. Somebody tell me what it is. Guess. No, it's not mole fraction. It's the South Carolina. No, it's not the South Carolina. It's the coefficient. Which coefficient? The stoichiometric coefficient in our balanced reaction equation. That's all it is. Remember, we did everything in our balanced reaction equation for 1 kilomole of fuel. And so those are just our stoichiometric coefficients in our balanced reaction equation. Where does the world get hard? It's in trying to make the calculation of what those H's are. That's where the world gets hard. And now we're having not just water coming in and water going out. We have fuel coming in and carbon dioxide going out and oxygen coming in and water vapor and carbon dioxide. Things are getting all mixed up. And it all depends on this word right here. Can we even pronounce that word? What's that word? Datum. What does that word mean? Straight out of Wikipedia or the internet search, it's the fixed starting point of a scale or of an operation. It's where we start, or the consensus of many people that went before us that have all probably passed on, because this has been ironed out in science and engineering for many years. You know, it's been done, is where they're going to agree to start measuring energy when you have things changing molecular structure and undergoing combustion and reactions. So that's the key. So they said, well, let's all agree. Let's kind of pick the standard temperature and pressure. Oh, that's nice. And now we have to say when these elements are stable. And we'll say, oh, that gives us a reference state to start our energy or enthalpy. That's where we'll fix it to be equal to 0. And this can be very confusing because people still struggle with, what does it mean? You know, how can I get a negative enthalpy for steam or a refrigerant? Well, somebody had to pick a starting point, and then you can get negative values. So this is the key term, enthalpy of formation. We'll pick up there next time. We have to understand the enthalpy of formation. And once we understand that, then we can come in and make calculations here. Thank you very much.